Hello everyone, this is Vatsal Chabe. Today we are going to talk about the DSP Lab 5. Uh, so let us try straight in. So in this experiment we will try to estimate the respiratory rate by extracting the respiratory signal from a collected PPG by using a fast Fourier transform method. So what is fast Fourier transform? Fast Fourier transform is essentially the same thing what we do in DFT, but the way it is implemented is slightly different. In this case, rather than by using the brute force method which we have always used for calculating the DFT, we'll be using the divide and conquer paradigm. In this case, we split our n point DFT into two n by 2 point DFT. As you can see here, this is a n. We have split it into two n by 2 DFTs of the even sequences, that is x of 2r, and the odd sequences x of 2r plus 1. So since common DFT has a complexity of O(n) square, and once we reduce it to n by 2 one step, we can keep on doing it further and further till we reach only 2 point DFT. So the net complexity of FFT will turn out to be O log n rather than being n square. So FFT is not a new algorithm, essentially the same thing as DFT, only the way it is implemented is different. So, coming to the experiment, PPG signal is superimposed with the respiratory signal. So what we can do, we can take a moving average filter to smooth out the noise. In my code I have not done it, but we can do it. Then the FFT of the signal is calculated. Here we are using the FFT library in Arduino to calculate the FFT, since the implementation is a little tricky to write by yourself. Now once we get the FFT, we know that the respiratory signal lies in the range of 0.5 to 0.5 Hz, whereas PPG signal lies in the range of 0.5 to 5 Hz. Once we know these frequency values, in the FFT spectrum, we can determine the value of index k, the particular index at which both the frequencies, the index at which 0.5 Hz occurs, such that the frequency spectrum below which will give us the respiratory signal, and frequency spectrum after it will give us the PPG signal. After getting the respiratory signal, we will find the maximum frequency point, and that maximum frequency point will give us the frequency of the respiratory signal, that is number of respiration cycles in 1 second. And if we multiply it by 60, if we multiply it by 60, we'll get the respiratory rate, number of respiratory cycles in a minute. Now coming to the code, so all the code can be found in the history. Separation of PPG and respiratory using FFT and respiration rate calculation. Hash include Arduino FFT.h. This is the Arduino FFT library which we are using for calculating FFT. This is our input signal. This UN16 is samples, the number of samples. Unsigned 16-bit integer we have used for the number of samples, and it is 1024. This should always be in powers of 2, because FFT needs a signal in power of 2 such that we can keep on decomposing it to the value of 2. Fs is the sampling rate, 6 size is the number of samples we had originally in our sample. So coming to the 2, here we define V real and V image. V real is the real part of our input signal, and V imaginary is the imaginary part of our input. So for I0, I less than samples, so till I is less than the signal size, we copy the real part to V real. After that, everything V real is 0 and all the imaginary part. Coming to the FFT computation, FFT.compute V real, V imaginary, samples, and FFT forward. This is a keyword which determines that we want to take a FFT. Now index is equal to 20. This is the index value at which 0.5 Hz occurs. So all the frequency samples below the index 20 Hz correspond to the respiratory signal, and all above 21 Hz correspond to the PPG signal. The respiratory real, respiratory imaginary, and PPG imaginary. less than samples by 2. We are going to samples by 2 because if you see here, we are taking the values from behind also. In a symmetric manner, we are taking the values. Since the FFT is symmetric, x of 0 is equal to x of n samples. So if we go halfway and take both the samples from both the sides, we'll be done. So when I less than index, real part of respiratory signal is real. Real part of respiratory signal samples minus I minus 1 is real samples minus I. So essentially we are taking both ends of the spectrum, 21 index 0 to 21 from the starting and 0 to 21 from behind. We are doing this because FFT is a symmetric signal. Similarly for PPG, this entire region will be 0. And for other indices like from index 21 to 1024 minus 21, we are taking the PPG to be the V real value, V real, and the PPG imaginary is V imaginary, PPG imaginary, and the real part of the respiratory signal is 0 in the middle, so is the imaginary part of the respiratory signal is 0 in the middle. Now we'll convert this complex values spectrum to a magnitude. So FFT dot complex to magnitude, V real, V imaginary samples, respiratory real, respiratory imaginary, FFT dot complex dot magnitude, PPG real, PPG imaginary, PPG dot sample. Now if we want to calculate the frequency, we need the peak, the frequency at which the spectrum of respiratory is at peak. So we can do this by FFT dot major peak, res real sample. This is the number of samples, this is sample. So this will give us the frequency at which the maximum frequency occurs in the respiratory signal spectrum. We can multiply it by 60 to get the respiratory rate. These commented code can be uncommented to find the inverse FFT. Like if we find the inverse FFT here, this is FFT reverse, and this of the PPG, this is FFT reverse of the respiratory signal, and we can plot it to see how the curve translates in time domain. But for this, we have to comment these all out. If we uncomment this, we have to comment all these out, because this complex to magnitude does in place computation. So res real, it will these real and imaginary part will convert to magnitude and place it in the res real array only. So if we do this and then do inverse FFT, we'll get some garbage results. That's why we should comment this out first and then run this. So coming to the results, this is our original sample with PPG and respiratory superimposed. Now when we took the spectrum, this is the PPG spectrum, this is the respiratory spectrum. So if you see, this is the part from 0 to 21 index where we are having the respiratory sample. This is all 0, and then towards the end we'll again get the respiratory spectrum. Similarly for PPG, in the middle we get all the values, and towards the end where there is respiratory, there is no. Similarly, the recovered signal when we plot, and just plot this by uncommenting them, we'll get the PPGs as this and the respiratory signal. I also wrote a MATLAB script similar to this for validation purposes, which can also be found here, and its plot can be shown here. This was the actual PPG, this is the FFT in 0 to 21. Here we are removing this part and this part to get the respiratory signal, and if we take only this part, get the PPG spectrum. So FFT of the PPG removed, this and this, and all the things in the middle we have turned it 0. FFT of the signal with respiratory removed, this and this 0. The entire thing is still present. Extracted PPG is still, extracted respiratory is still. Now to calculate the respiratory rate, FFT on Android will give us 16.56, whereas FFT on MATLAB gave us an error rate of 3.5%, which is fine. So coming to the conclusions, through this experiment we implemented the fast Fourier transform and saw how can we use it to distinguish between two signals varying in frequency, and how can we extract them from a superimposed signal. Once we get the signals extracted, we can do our previous analysis to find a time period frequency. Thank you.